Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome back to the session. I'd like to talk about a set of awards that we have. If you missed the opening presentation, you may not have heard about this, but this year we introduced a set of awards for reviewers who did an outstanding job in their reviewing. So we had 1,200 reviewers, and we gave 100 reviewer awards to reviewers based on nominations from the area chairs on the basis of the quality and depth of the reviews, and also their engagement in the discussion period, and just in general their efforts to make this a great conference. So, I'd like all of us to thank, especially these 100 reviewers who did a fantastic job for NIPS. And of course, we appreciate the work that the other 1,100 reviewers did as well. But it's great to see people doing their job well above and beyond the call of duty. So I'll leave this up for a minute. You can spot your name if you're there. And it's also on the web page already. Okay. All right. There's another innovation that Max and I introduced this year, which is to have the anonymous reviews and author rebuttals of all accepted NIPS papers available online. And thanks to the efforts of many people, including Chris Heisen especially, we now have these on the website. So if you go to http://papers.nips.cc and you click on any paper, you can actually read the reviews and the author rebuttal, and I think it helps put the perspective some of the work that was done, and also provides us with a lot of good information about the review process, and just more openness and transparency to the whole thing. So that's already available. The paper site is in beta right now, and the new features are being added, but all of this year's papers with the reviews and author rebuttals are there for you to see. Okay, so with that, I'm going to pass it over to Emily Fox, who's chairing this session.
Okay, welcome to the last session of the day before the posters. Just a few minutes to rest before we get the first talk. Okay, so the first talk is by Pierre Baldi on understanding dropout.
So in addition to the poster, let me say that there will be also a second talk by Peter Sadowski on our work with no overlap to the present talk in the workshop on randomization methods. So you all know what dropout is. It's a randomization algorithm for training neural networks. It proceeds online, and for a given input vector, you delete neurons at random independently in the network, typically with probability 0.5. You can do it in the input. The recommendation is deletion with probability 0.2. You bring the next example. You do it again in a completely random fashion using backpropagation. And the important thing, of course, is to share weights between one example and the next. And at the end of the process, which is convergent. At prediction time, you multiply all the weights by 1/2 to get your predictions. And the inspiration behind dropout is to prevent the co-adaptation of feature detectors. That's in the title of the paper by Internet al. That describes dropout, in order to have neurons that are uncorrelated with each other. And it can be viewed, at least intuitively, as a cheap way of training the ensemble of all possible networks. You can immediately ask a lot of questions about dropout. It looks like a clever hack at first sight. So you can wonder whether you could use dropout on the connections, whether you could use other values of P. Is P05 optimal? What about using different P's in different places? What kind of average is dropout really computing, etc., etc. So we're going to try to answer some of these questions. To do that, it's good to start with simpler networks, linear networks, and to have a good formalism for that. And so obviously you can write dropout in terms of Bernoulli random variable, the deltas here. There is a delta JL for neuron J in layer L. And all these delta JL are independent of each other and can be 0 or 1 with some probabilities. And of course, with the same formalism, you can introduce dropout on the connections if you want. And all the results I'll present with minor modifications are true for dropout on connections. So from now on, I'm just going to stick with dropout on the units. So what kind of averaging dropout is doing? How can you compute in a linear network the average activity of all the unit in this stochastic network where every unit is flipping on and off? Well, it's very easy to do for a linear network because the expectation is linear with respect to sums. It's linear with respect to products of independent variables. And so you get this very nice formula that allows you to compute the expectations of any linear neurons. And you see that the weights are multiplied by the dropout probabilities as in the prediction networks. So it's easy to solve linear networks for dropouts. I'll want to make 3 remarks, however. If you were to compute this expectation by writing the sum over all possible networks, it would be an extremely difficult problem. So that's the beauty of the expectation operator. The second thing is that if you want, you can compute all the variances and covariances between any pairs of units just by a similar feed-forward propagation from the input layer to the output layer, using, again, the properties of the expectation, which is quite nice. And the last observation, which is less obvious, is that this equation here, where you have linear propagation and multiplication by numbers at the nodes, should look familiar to some of you because that's exactly what backpropagation is. So if in backpropagation you use standard logistic units, derivatives are between 0 and 1, and you can view them as probabilities. So what I'm trying to tell you is that backpropagation can be viewed as computing the expectation of the linear backward propagation over all possible dropout of the neurons, where the dropout probabilities are the derivatives of the logistic function in the forward network, which is quite interesting, and Peter Sadowski will tell you more about that in the other talk. Linear networks are for babies, as reviewers point out, so let's look at nonlinear networks. Consider a deep network of the sigmoidal neurons. We would like to do the same thing. The problem is that the expectation doesn't go, or at first sight, doesn't go through the sigmoid. In reality, it does, but one has to do some math to discover that. So let me try to show you why it's computing the right expectations, even in the sigmoidal case. For that, I need to introduce some notation. So imagine that you look at one sigmoidal unit to begin with. It has different outputs, so 1 to OM under dropout, but it could be under other things, under different inputs, or even under Gaussian noise in the inputs, on the weights, etc. You look at the complements, the 1 minus OI. You have a probability distribution over these numbers, and you can define the obvious expectation, the expectation of the complement, C prime, the geometric mean of the complements, and then this strange quantity, which is the normalized weighted geometric means, G over G plus G prime. And it's easy to show with a little bit of algebra, 2 lines of algebra, that the sigmoidal, the logistic functions, have these remarkable properties. property that the NWGM of the logistic function is the same thing as the logistic function applied to the expectation. So you see here that it allows, assuming that the NWGM is a good approximation to the expectation, this is what allows you to propagate expectations from outside the sigmoid to inside the sigmoid. So again, if the NWGM is a good approximation to the expectation, well, let me back up. You may wonder what is the class of functions that satisfies this property, and you can show that it's exactly the class of logistic functions. That's an interesting result to know, but not the main point here. So if the NWGM is a good approximation to the expectation of a neuron under dropout, you get these three essential recursive equations where you would like to compute the expectation of all the neurons in the sigmoidal network. You approximate this expectation with the NWGM. That allows you to put the expectation inside the sum and then propagate to the layer below where you start again. So for this to give you a good estimation of the expectation, you need two things. You need the NWGM to be a good approximation to the expectation, and you need the fact that when you do this on many layers, the errors, the approximations do not cause a bias or some errors to grow up. So why is that the case? Well, you can look at the geometric mean, and there are results that show that the geometric mean is already a good approximation to the expectation by itself. It's less than the expectation by convexity. There are inequalities, for instance, by Cartwright and Fields that give you bound to the difference between the expectation and the geometric mean. And there are other inequalities, chi-fan inequality, for instance, that show you that if the numbers, if you had a unit that had low values between 0 and 0.5, then the normalized geometric mean is between the geometric mean and the expectation. So it's a better approximation to the expectation than the geometric mean. So to look at this more deeply, one can do an expansion of these numbers, and you can do expansion around 0, 1, or 0.5, or around the expectation. We've done all of them using the standard series and products of series. And the bottom line is that the geometric mean to a second order of approximation is equal to the expectation minus the variance. You can do the same thing for G prime. It's going to be 1 minus the expectation minus the variance. And so at the end of the day, you get this estimate for the normalized geometric mean, which is that G over G plus G prime is, to a second order approximation, E minus V over 1 minus 2V. And if you look at the difference between the expectation and this quantity, you get this approximation, which can easily be bounded by these numbers. This is because the variance of a variable between 0 and 1 is always less than the variance of the corresponding Bernoulli variable. So it's less than E times 1 minus E. And you can plot these functions. They depend only on the expectations. You get very nice curves that are quite close to 0. This maximum is at about 0.15. So this is a theory that tells you that the NWGM is a very good approximation to the expectation, and in fact you can bound the errors. Now, some of you don't believe in math, so let's look at simulations. We replicated the Internet results by taking exactly the same network, 4 layers of 1200 units, dropout at 0.5, etc., etc. Everything is same NIST data, and this is what you get. This is at the beginning of learning. This is at the end of learning. I'm plotting the difference between the expectation of a unit computed by Monte Carlo simulation and the NWGM. You can see that the red dots are very close to 0. The blue dot are the approximation, second order approximation. You cannot really distinguish them from the red dot. And these are the bounds. Those two curves that I showed you are bounding this. So this is showing you that the theory works well. You can do expansions around E. You're going to get, it's hard, you really need to look at these curves, but you get approximations that are more precise, but that are correct on a narrower range than if you do expansions around 1/2. You can also show that the NWGM is distributed around the expectation roughly like a Gaussian. Sometimes it's larger, sometimes it's smaller. And this explains why the error don't accumulate when you do it on multiple layers, because when you are summing things, if sometimes you're higher, sometimes lower, things tend to cancel out in the averaging process. I'm skipping some details here. This is the same plot, but plotting the difference between W. W is the deterministic values that you have in the network that you use at prediction, which is slightly different from the NWGM at each node. And you can see that these differences, these are histograms computed over all the neurons in each one of the 4 layers. Each row corresponds to a layer. These histograms are very close to 0, again showing that dropout does indeed give a very good approximation to the ensemble. You can also compute high order moments like we did in the linear networks. And essentially, if 2 neurons are not connected to each other, you can estimate the expectation of their product just by taking the product of the W's. And that will give you a very good approximation. You can see that the histogram is very concentrated around 0. And this is essentially equivalent to saying that all the covariances are very close to 0 for neurons that are not directly connected to each other. We have expressions also for those. Everything I told you so far has to do with the static properties of dropout. That is, you fix the weight at a certain time, and then you look at how well the network, the deterministic network is approximating the ensemble, all the average values computed over the corresponding dropout. Now I want to look briefly at the dynamic properties of dropout, what happens during learning. And again, let's take a very simple case of a linear network. So this is the error function in the dropout network, which depends on the dropout Bernoulli variable. This is the error function of the ensemble network. And you can, of course, take the gradient of the dropout network. You get this expression. And you can compute the expectation of the gradient of the dropout network. And what you get is this quantity here. These are equalities. There is no approximation here, which corresponds to this function here. So in other words, you see that in the linear case, what dropout is doing is stochastic gradient descent with respect to an error function, which is the error of the ensemble network plus a regularization term, which is a quadratic weight decay Gaussian prior type of term with a W square, but with an interesting coefficient, adaptive coefficient, which is, in this case, is just the variant of the Bernoulli variable times the square of the input of the corresponding input for that value. So that's what you see in the linear case. Does it go through to the nonlinear case? Well, roughly yes, because again, you have the gradient. This is a single sigmoidal neuron. You have this expression for the gradient, the error times the presynaptic activity. Your problem is that there is some dependency between these two terms when you take the expectation. So what you have to do is a Taylor expansion of this quantity, which is the sigmoid. You do a standard Taylor expansion to separate the term that is dependent as a dependency with this term from the other ones. So that's where you have a first order Taylor expansion. So now you have an approximation if you want, but you get this expression, and again, it's the same result. So dropout is doing is a very nice way, if you want to, of regularizing your network with the quadratic penalty terms on your weight, plus very nice coefficients that essentially are dependent on the variance of the neuron that is sitting below you. So you can say that dropout tends, among other things, not only to reduce the error, but also to reduce the variance of the neurons throughout the network. And this explains, or we think it explains, why dropout has a tendency towards finding sparse representations, because those are the ones that reduce the variance. Indeed, in this 4-layer system that we have simulated, you can see that if you plot the histogram of the activities at the end, you have a very sparse representation. This explains also why drop-in doesn't work. By drop-in, I mean the symmetric algorithm where instead of setting 50% of the neurons to 0, you set 50% of neurons to 1. You may think that it's completely symmetric and it should work. It doesn't work at all if you try it. And this has to do with the fact that it doesn't, of this variance shrinking effect. I'm going to skip this. I'm out of time. Some of you tell me that there are no applications of dropout and deep learning in computational biology. It's completely false. These are results from the last CASP experiment, which is the CFARM NIST of protein structure prediction. The top two entries are deep learning in the contact map prediction category. We have applied also deep learning in chemoinformatics to predict properties of small molecules. You want to predict whether a drug is soluble or a small molecule is soluble. You can build neural networks that are crawling the chemical structure of the small molecule in the same way that you can have neural network crawling parse tree in natural language, etc. Well-known recursive neural network techniques, and they work quite well. So in closing, I think we had a lot of questions about dropout, and I hope I have convinced you that we have a mathematical framework that can answer at least some of them. We have other results that I haven't been able to show you that are in a long technical report that you'll be able to get from our website. But in my opinion, what is striking is that although dropout looks like a hack at first sight, there is in fact a lot of mathematical structure behind it, and I don't think this is by chance. I think dropout is much more than a clever hack. Thank you.
Okay, we have time for some questions.
So recently in discriminative setting, the most used activation function is rectify linear unit. So I just wonder if you have done analysis for rectify linear unit instead of sigmoid.
We have thought about it, but we have no results to report so far.
And actually another thing which is really confusing for me is why dropout doesn't work that well for convolutional neural networks.
I don't have an answer either.
Okay, thank you.
Well, when you say convolutional network, you have to be careful how you do dropout with the weight sharing. So do you share the dropout across the shared weights?
I don't know how to do it correctly. I tried, let's say, several random experiments, and any of them worked.
Well, I think the key, you have to share the dropping. If you do weight sharing, you have to drop the same thing across the different positions, right? I think that is key. If you haven't done that, I think that's a good explanation of why it didn't work.
Okay, I'm not sure if I have done it or not. Okay, thank you.
So my friends here and I have the state-of-the-art on CFAR 10 and Street View house numbers with a single convolutional neural net. You can do better than us with ensembles. But we found that dropout was critical for good performance in convolutional nets. So it absolutely does work for convolution.
Good. We had real-time answers here.
We have time for one more quick question, if anyone has it. Okay, let's thank the speaker again. Okay, our next speaker is Roger Gross, and he's going to be speaking on annealing between distributions by averaging moments.
Okay. This represents joint work with Chris Madison and Ruslan Salkutinov. So would you trust the outputs of a machine learning algorithm that's never been validated on held out data if someone just tells you that they've looked at the results and they seem pretty nice? Well, this is unfortunately the position that we're in with density modeling. Because it's so difficult algorithmically to evaluate a lot of generative models, we often use cruder techniques like just looking at samples from the model. And in the case of undirected graphical models, the reason that evaluation is so difficult is that they're given in terms of an unnormalized probability distribution, and in order to evaluate likelihood in held out data, we need to somehow estimate this intractable partition function. So a lot of the algorithms that people apply to estimating partition functions are based on this idea of designing a sequence of distributions that bridge between a tractable initial distribution, P init, and an intractable target distribution, P target. Annealed importance sampling is the particular algorithm that I'll focus on, but there are a number of others that have been proposed in the same category. And the choice of distributions that people almost always use is geometric averages of the initial and the target distributions. This is generally chosen because it's very easy to do. It often involves just averaging parameters of the models. And geometric averages are often justified in terms of a sort of annealing effect, where if you start with a uniform distribution, then your distributions become gradually more and more peaked as you reach the target distribution. And so it's sometimes tough to think about discrete sequences of distributions. So let's imagine that we have a space P of probability distributions parameterized by theta. And we think about a continuous annealing path, which is just a mapping from 0, 1 to space P. And then we choose a set of values beta, the inverse temperature parameter, spaced somehow along this path. And that defines a sequence of intermediate distributions. But unfortunately, it doesn't always work out nicely. And so sometimes we get a situation more like the following, where the model has a phase transition where the distributions change very quickly as a function of the parameters. And so you wind up not putting enough distributions around the phase transition. And so often applying AIS in practice requires carefully tuning an annealing schedule. In fact, every time you train a new model, you have to tune a new annealing schedule. So it's a very large amount of work. And another issue with geometric averages is that it can often do some fairly unintuitive things. So here we have initial distribution and target distribution, which are both multivariate Gaussians. So you can ask yourself what the annealing sequence would look like. The answer might be surprising if you haven't dealt much with AIS. In fact, it sort of curves around and then hovers for a while in a very weird region, and then eventually reaches the target distribution. Here's another example from restricted Boltzmann machines trained on MNIST. On the left, we see an approximate set of samples from the target distribution. And on the right, we have the 9 independent Markov chains, which are passing through the geometric average annealing sequence. And what we see is that they decay down to blank images. And then eventually, right at the end, some digits start appearing. And so this is kind of funny. We'll see why this happens later on. And so the algorithm that I'll be talking about today, annealed importance sampling, is something that people very often use for estimating partition functions. And so you have a sequence of unnormalized intermediate distributions, and for each of them you have an MCMC transition operator which preserves it as a stationary distribution. And you start with an initial sample from the initial distribution, and you alternate between taking MCMC steps with respect to each of the operators and computing importance weighting updates. And at the end, you wind up with a weight, which is an unbiased estimator of the partition function of the model. And so you basically run this a number of times and average the weights, and that gives you an unbiased estimator of the partition function. And so what's nice is that it's an unbiased estimator. What's not so nice is that often we find it more interesting to think about log partition functions, because partition functions vary over many orders of magnitude. And AIS gives a biased estimator of the log partition function. By Jensen's inequality, it generally underestimates it. And this is problematic in the context of model selection, because if you underestimate the partition function, that corresponds to overestimating the likelihood of the model. And so you know that either you have a really good model or a really bad partition function estimator. And we can ask, is this a problem in practice? Here's an example of evaluating the partition function of an RBM that was trained in MNIST. So we see AIS estimates with different numbers of intermediate distributions using 2 different annealing paths. And they differ by 17.5 nats, which means that one of them is telling you that your model is e to the 17.5 times better than it actually is. So I'm going to present an alternative sequence of intermediate distributions based on averaging moments. So exponential families are parameterized equivalently in 2 different representations. There are the natural parameters, and there are also the moments, which are just the expectations of the sufficient statistics. And geometric averages has a nice interpretation for exponential families in terms of averaging the natural parameters of the distribution. And this is probably why people use it so often. You just have to linearly average parameters. So what we're proposing instead is a fairly simple modification, seemingly, where we, instead of averaging the natural parameters, we average the moments. And to give an intuition for this, here's the geometric average sequence again for multivariate Gaussians. For moment averaging, what it does is kind of interesting. It linearly interpolates the mean of the distribution, but it also stretches out the variance in the direction connecting the two distributions. And this stretching out is a useful property because it increases the overlap between consecutive pairs of distributions as the mean is shifted. And so why do they take this form? Well, we can look at the two different annealing paths in terms of variational formulations. So each of the intermediate distributions optimizes a weighted sum of KL divergences to the initial distribution and the target distribution. And they minimize the weighted sum in opposite directions. And so geometric averages is the direction that gives you very constrained distributions. And so it's effectively taking the intersection of the initial and the target distribution. And so if you extend out the two Gaussians, that's where they intersect. Whereas moment averages likes to capture all of the mass of the distributions. And if you're using an algorithm that's based on importance sampling, you generally want your proposal distributions to be very broad so that they don't miss any important mass. And so that's what moment averaging is trying to do. Another way to analyze annealing paths is to look at how the error behaves asymptotically as you add more and more intermediate distributions. So if we assume perfect transitions, which means that each of your MCMC transition operators returns a perfect sample from the distribution, then the bias of the log weights of AIS decomposes as a sum of the KL divergences between each successive pair of distributions. This is kind of intuitive because KL divergence is a distance measure, and you want each pair of distributions to be very similar to each other. And if we assume perfect transitions, then the bias of the log weights is also monotonically related to other criteria, such as the variance of the weights or the variance of the log weights. And so we can say that the goal is to minimize the sum of the KL divergences between each pair of distributions. So because it's tricky to analyze discrete things, we can think about continuous paths and space the intermediate distributions more and more finely along the paths. And as you do that, the bias approaches zero, but if you rescale by the number of distributions, it approaches a particular functional on the curve, which intuitively it pays a high cost when the distribution changes very quickly as a function of the beta parameter. So this is related to ideas from information geometry, and it's also the same functional which was discovered in the context of path sampling by Gelman and Meng. And so it might seem a bit clearer when we think about the optimal schedules along the paths. So this is something that this analysis will give us. So basically the cost under an optimal schedule is given by L, which is the path length on a Riemannian manifold where the metric is Fisher information. And so we can visualize it. Here's a visualization of a space of univariate Gaussians parameterized by mean and standard deviation. And the circles are the unit of the Fisher information metric. And the path length essentially corresponds to the number of the Fisher balls that it crosses. And so we see that geometric averages just run straight across the bottom where the balls are packed very densely, so it pays a very high cost. Whereas moment averages curves across the top by increasing the variance, thereby paying a lower cost. And Gelman and Meng actually analyzed the optimal path in this particular example, which corresponds to a geodesic in the space. And interestingly, the two paths have a very similar form. They're not identical, but they're doing similar things. And so quantitatively, we can look at how they perform in the Gaussian example. And so geometric averages with the linear schedule requires O of d squared distributions to achieve a given level of accuracy. And same if you use an optimal schedule. Moment averages with the linear schedule also requires O of d squared. But if you use an optimal schedule, it drops to log d squared. And this is actually within a constant factor of the optimal path. It's not always easy to determine the optimal schedule. But what we can often do, if we have a set of points where we know the natural parameters and the moments, we can consider paths which are piecewise linear. So we have a bunch of bins, and we can allocate intermediate distributions however we want to different bins, but they need to be spaced linearly within a bin. And there's an analytic formula for the optimal piecewise linear schedule. And there's this caveat that this analysis assumes perfect transitions, and the mixing effects can often be fairly significant. So now we turn to some experiments. So we can basically run AIS using the different paths and compare the estimates of the log partition function. And so here it is for the multivariate Gaussian example I showed earlier. We see that moment averaging is able to estimate the log partition function accurately with very few intermediate distributions. This is a normalized model, so the log partition function is 0. And geometric averages requires about 100 distributions in order to get close. And this is true whether you use Gibbs sampling or whether you have perfect transitions. We also looked at restricted Boltzmann machines. These are Markov random fields with the bipartite structure. And they can be represented as exponential families where the natural parameters are the weights and the biases. And the moments are the average activations of the visible and hidden units, as well as the average co-activations. So in order to do moment averaging, it's unfortunately not tractable to do exactly, but we can approximate it reasonably well. So we need to estimate the moments of the target distribution. We can do that by running a Gibbs chain for a long time and collecting the statistics. And we need to estimate, or we need to fit these intermediate distributions, which is a moment matching problem, essentially fully observed MRF parameter learning. And we can do that using persistent contrastive divergence. Fortunately, the distributions don't need to be very accurate, so we can use a much smaller number of steps than would normally be required for training RBMs. And because we don't want to solve for every RBM on the path, we just solve for a few and then interpolate between them using geometric averages. So we looked at an RBM with 20 hidden units trained in MNIST using PCD. And so with 20 hidden units, you can compute the exact partition function by exhaustively summing over all of the configurations. And we see that moment averages is able to accurately estimate the partition function with a lot fewer intermediate distributions when Gibbs sampling is used as the transition operator. Actually, if you use perfect transitions, then the estimation problem turns out to be fairly easy, suggesting that mixing is a very large part of the difficulty of evaluating partition functions. We looked at cases with 500 hidden units trained with 3 different algorithms. And here it's impossible to exactly evaluate the partition function, but because the estimators are both stochastic lower bounds, we can figure that whichever one of them returns a higher value is closer to the truth. And it's actually kind of interesting that every RBM seems to be its own partition function estimation problem, and it could be very different in terms of which algorithms seem to work well. But in general, we see that moment averages compares pretty favorably with geometric averages. And so here's the example again of the 2 different paths for one of the RBMs we looked at. And so geometric averages decays down to blank images, even though blank images had probability 10 to the minus 7 in the target distribution. And this is because the initial distribution put uniform distributions in the hidden units. And so whatever part of the configuration space has the hidden units closest to uniform gets dramatically upweighted. And this happened to be the blank images. With moment averages, we actually get sort of blurry, jumbled together digits throughout the entire path. And we actually get very nice diversity throughout the entire path. So to conclude, if there's one takeaway message, it's that the choice of annealing path is a key design decision when you're trying to estimate partition functions. And I would argue it's on par with choosing good MCMC transition operators. So our main contributions are we presented a theoretical framework for analyzing different annealing paths. We presented a novel annealing path based on averaging the moments of the initial and the target distribution. and we showed that the moment averaging path is able to effectively estimate partition functions of RBMs. And we believe this work is relevant to a wide number of algorithms which are based on sequences of distributions, including parallel tempering, which is often used for training Markov random fields. So our poster session, ominously, is Friday the 13th. So.
Yeah, so questions?
Did you apply this annealing path for when you have a phase transition for the problem you mentioned at the beginning, the moment averaging?
So we haven't looked directly at phase transitions. So there are sort of multiple reasons that phase transitions can hurt you. And so some of it falls under the analysis of perfect transitions. And so in that case, the optimal scheduling would tell you where to allocate your distributions. But there's a much bigger effect, which is that during the annealing process, mixing starts out very fast and then gets much slower. And at some point, different modes might diverge, and then it's very hard to reduce the variance that's caused by misallocating things between different modes. And so moment averages, I guess, tries to capture tries to allocate things relatively fairly between different modes, which sort of falls out of the variational analysis. I think that's a fairly significant part of the results. And we actually haven't noticed much of an improvement from the optimal paths themselves falling out of the perfect transitions analysis, which is kind of surprising because that's where most of the work is focused in the past in terms of coming up with annealing schedules.
Okay, David.
So I was a little surprised by your mentioning that you don't have to worry too much about getting the marginals very accurate.
Mm-hmm.
So you said you use this contrastive procedure. Can you tell a little bit more about why?
So that was mostly an empirical fact, but you can imagine that what's really important is that these intermediate distributions can capture all of the relevant areas of mass. So they just don't leave out anything important. But because you're inserting a lot of intermediate distributions in between your moment averaged RBMs, it's actually able to sort of, as long as they're similar enough to each other, annealing using the geometric paths should clean up a lot of the variability.
Okay. I have one quick question, maybe while Jeff is setting up. Just in terms of computing these moments in more complicated models and sensitivity to inaccuracies of that, have you thought about that and what the effect is?
It's certainly something to look into, and something that we're trying is actually running this in the context of parallel tempering, in the context of training models, so you can jointly estimate moments like while you're training, and shouldn't give you too much overhead compared to what you're already doing for training.
Okay, let's thank Roger again. Okay, our next speaker is Jeff Miller, and he's going to be speaking on Dirichlet process mixture and consistency for the number of components.
All right. Thanks, Emily. So oftentimes you have data which may come from multiple groups, and a finite mixture may seem like an attractive model. A problem with finite mixtures, though, is that usually you don't know how many groups there are, and it can be really hard to choose an appropriate number of components to use for your mixture. So the nice thing about Dirichlet processes is that they allow you to construct a very flexible Bayesian model that can, in a sense, adapt to the complexity of your data, and it can fit the data distribution no matter how many components there may have been. Often, though, there's an interest in, let's see, it's not clicking. Often people are interested in knowing the number of groups that are in the data. And recently, Dirichlet processes have been used to try to infer sort of how many groups there are. And I'm showing some examples here, and it's been done in quite a wide variety of different applications. So, for example, there's a recent study of West African forest geckos in which they took samples from a whole bunch of these geckos and they looked at certain genetic markers, and then using a Dirichlet process mixture along with some other tools from population genetics, they concluded that there were at least 4 different species of these geckos, whereas previously it had been thought that there was only 1 species. So the fact that this is being done so frequently raises an important question, which is we know that the Dirichlet process mixture is a great flexible prior on densities. There's some really nice theoretical results showing that the posterior on the density concentrates at the true density. But what if you're actually interested in the number of groups in your data? And so if the data actually comes from a Dirichlet process mixture, then it's sensible to use the posterior on the number of clusters or components that are represented in the data for inference about the number of clusters. But what if the data actually comes from a finite mixture? So this is the question that we asked. If the data comes from a finite mixture and you use a Dirichlet process mixture, does that posterior concentrate at the true number of components? And as you probably could infer from the title of the talk, the answer is no, it doesn't concentrate. And the reason may be a little bit surprising, so stay tuned for that. So in a standard finite mixture model, you have some fixed number of components, k. Your weights are drawn, pi 1 to pi k are from a Dirichlet distribution. The component parameters, theta 1 to theta k, are from some prior. And then given the pi's and the thetas, your data is IID from the resulting mixture, just your standard sort of finite mixture. Now, in a Dirichlet process mixture model, you have infinitely many components. So and in a Dirichlet process mixture, the pi's are pi 1, pi 2 are drawn from a stick breaking process. The component parameters, theta 1, theta 2, and so on, are from your prior or base measure, as it's called in this context. And then, just like before, given those, the data is IID from the resulting mixture, which in this case is an infinite mixture. So to use sort of a restaurant analogy in a slightly different way than it's usually used, we can think of each component in the mixture as a table, and each data point as a customer. And given the weights, the pi's, each customer comes in and they choose to sit at a table with probability according to the pi's. So for a finite mixture, of course, we'll have finitely many tables or components, and some subset of them will be occupied tables. In a Dirichlet process mixture, you have infinitely many tables or components. But for a finite amount of data, only finitely many of the tables will be occupied. So in this little example I'm showing here, 4 of the tables are occupied tables. So what happens if we use a Dirichlet process mixture on data from a finite mixture? Well, there's quite a bit of theory for looking at the posterior on the density, and it's known that, in fact, it concentrates at the true density, often at the minimax optimal rate, so it's the best that you can do. And that's true not only for if the true density is a finite mixture, but actually for any sufficiently regular density. So there's some really nice theory and quite a lot of contributions by a number of people in this area. And further, there's a recent result by Long Nguyen who showed that, in fact, the posterior on the mixing distribution concentrates at the true mixing distribution in a certain sense. So, but what about the number the number of components? So let me go back to this slide for a second. If you're interested in the number of components, well, and you're using a Dirichlet process mixture, there's a little bit of a problem because your prior, you always have infinitely many components. So the posterior on the number of components is essentially a point mass at infinity. So what's often done instead is to use the posterior on the number of occupied tables for inference about the number of components that the data comes from. So this is the question that we addressed. So does the posterior on the number of occupied tables concentrate at the true number of components? So I'm going to show you some some experimental evidence, some suggestive evidence. Then we'll look at our main results, our theoretical results, and then I'll explain sort of the intuition behind the results. So ever since people have been using Dirichlet process mixtures, it's been observed that when you draw clusterings from the posterior, you often get some tiny extra little clusters. So here's an example. So on the left, I'm showing you data drawn from a bivariate Gaussian mixture with 4 components. And the data, each data point is colored according to which component it comes from. So we've got 4 nice sort of clusters there. On the right is the same data, and each data point is colored according to which cluster it is in a sample from the posterior of a Dirichlet process mixture. And you get these 4 nice, this way, 4 nice clusters, just like on the left, except there's this one data point here, which is in a cluster all by itself. And so if I show you some other samples, here's another sample. You get these guys over here are in a separate cluster. And I'll just click through some samples so you can sort of get a sense for what these posterior samples look like. Sometimes there's a couple extra points in a cluster. Sometimes there's just 4 clusters. And they're not always the same points that are in their own extra cluster. Okay, so if we look at the posterior predictive density, so on the left I'm showing you the true density, and then on the right, so this is the mixture density that the data is actually drawn from. On the right is the posterior predictive estimated from sampling from this posterior. And these tiny extra clusters, because there's so few data points associated with them, they have a negligible impact on this posterior predictive. And as a consequence, the posterior predictive matches the true density very, very well. So there's no issue there. But of course, if you look at the posterior on the number of clusters or the number of occupied tables, then as you could sort of see from those samples, it's putting significant amount of mass above the true number of components, which was 4. So from sort of green to cyan to blue to black, the amount of data is increasing, n is increasing. And it doesn't look like it's sort of converging concentrating at 4. Ideally, you'd want this to be concentrating to a point mass at 4. But this is just sort of empirical evidence. Maybe we just don't have enough data. It's sort of hard to tell what's going on. So what can we prove? So here's our main result. So under mild regularity conditions, if the data is IID from a finite mixture with k-naught components, and you use a Dirichlet process mixture, then the posterior on the number of occupied tables does not concentrate at the true number of components. And so with this little bit of math here saying that the posterior probability that the number of occupied tables is k-naught, that's not converging to 1. So of course that implies inconsistency. And here I just want to mention that we're assuming that the model is correctly specified in the sense that if the data is from a finite mixture of, say, Gaussians, that you're using Gaussians in your model. So there's a correct match between the family of component distributions. So we're assuming that the concentration parameter here is fixed. Sometimes the prior is put on that, so we don't have a result in that case. So this is for a fixed concentration parameter. This does generalize to Pittman-Ure process mixtures. And we have a paper posted on arXiv with the more general form of the theorem, if you're interested in that. In the NIPS paper, we gave a nice, I think it's a nice short proof of this inconsistency when the data comes from a univariate Gaussian with 1 component. And we showed that actually it's possible that that posterior, not only doesn't go to 1, it actually goes to 0 in certain cases. So it sort of can be severely inconsistent in that sense. So this implies, so our result applies to a pretty wide range of mixture distributions. So mixtures over a large class of continuous exponential families, including multivariate Gaussians and quite a few others, to essentially any discrete family. So it's a pretty general phenomenon. All right, so I want to emphasize that, I don't want to say that Dirichlet process mixtures are bad. They're excellent when used appropriately. And so in particular, as a flexible prior on densities, for sort of Bayesian density estimation, they're fantastic, and that's what the theory sort of supports, as well as empirical evidence. And but in that case, you're not looking at the latent structure. You're not looking at sort of the number of clusters, the component parameters, which data points assigned to which cluster. That's all nuisance parameters that's sort of integrated out, and you're just concerned with the density. Another case in which it's fine is, of course, if the data actually comes from a Dirichlet process mixture, then it makes sense. Then everything's correctly specified, and there's a match between the data distribution and the model. And so, just by the usual sort of Bayesian crank makes sense, and it works. But there's a big difference between that and a finite mixture. So what's the intuition for why this inconsistency happens? So usually what's thought, and what we originally thought, is that the issue was going to be that the prior on the number of clusters or occupied tables is diverging. So it's well known that if n is the number of data points, then the expected number of clusters goes at like a log n rate. But it turns out that that's not the whole story. And in fact, there's a sort of deeper reason why this inconsistency happens. That's not really the fundamental reason. So instead of looking at the prior on the number of clusters, you actually need to be concerned about the conditional distribution on the cluster sizes given the number of clusters. And if you do a little calculation, you see that this is proportional to the product of 1 over the sizes. So if you think about that for a minute, you'll see that it's the same shape as a Dirichlet distribution, a t-dimensional Dirichlet, in which all the parameters have been taken to 0. And if you have sort of the intuition for what that means, as those parameters are going to 0, the distribution is becoming more and more concentrated in the corners of the simplex. And in this case, it's a distribution on a finite space, so you can actually take that limit and it's still normalizable. But what you can see from that intuition is that distribution is extremely concentrated in the corners of this sort of simplex. So for example, when you have t equals 2 occupied tables, if you look at that distribution, so here I'm showing you the CDF for increasing n, and what you can see from the CDF is that it's putting a significant amount of mass, so let me show you here, with that, if we look at the size of one of those two tables, there's a significant probability that it's either extremely small, like one person basically, one customer at that table, or essentially all of the customers are at that table. So what this is telling you is that the DP prior really likes to have at least one or more tables with very, very few customers. So that's the prior. Now the posterior is proportional to prior times the likelihood. And the key thing is that the likelihood, it turns out, doesn't really mind that much having these tiny extra clusters. It's not significantly reduced. And so what sort of happens, that's actually the hard thing to prove. So what ends up happening is that the prior sort of says, I'd really like to have a tiny extra cluster, and the likelihood says, okay. And so you get these tiny extra clusters, as has frequently been empirically observed. So are there any good solutions to this problem? So one thing so our result was for the case of a fixed concentration parameter. One thing which is often done is to put a prior on the concentration parameter. So you might wonder, will you get consistency in that case? And we don't have a proof in that case, but we would conjecture that you could still have this type of inconsistency. Another thing which is sometimes done to directly combat this problem is to just sort of discard those extra tiny clusters, those tables with very few customers, when you're computing, say, an estimate of the number of components. Now, that we don't have a result for, but we would conjecture that you could get consistency in that way. So that looks from our intuition like it might work. A third option, which is known to work, is to take a finite mixture and then just put a prior on the number of components. So this is sort of the natural Bayesian thing to do. It's not a new idea. And in fact, going back to, at least back to Nobile in 1994, it's been known that in principle, this does give you consistency for the number of components. The caveat is that you need the component distributions to be correctly specified. And that's sort of an unreasonable assumption, because in practice, you wouldn't really expect your data to come from a finite mixture from a known family of known parametric family. So I want to emphasize this point that if you're interested in the number of components, you really need to be careful about this misspecification, because, for example, if you're using a Gaussian mixture model and the data is from something which is very, very close to a finite mixture of Gaussians but slightly not, then you're going to need more and more components as the amount of data increases in order to fit that distribution. And so the posterior on the number of components is going to be very sensitive to that type of misspecification. So as a general sort of caution to people who are interested in the number of components, I would urge you to think about whether misspecification is an issue for your application, and if so, to think about if there's some other measure of heterogeneity that might serve your purposes just as well. So in summary, the Dirichlet process mixture posterior on the number of occupied tables should not be used to estimate the number of components in a finite mixture. The poster is number 37 this evening, so please stop by and I'd be happy to chat.
So we have time for some quick questions.
Thanks. So as you say, DPMMs might still be good for a bunch of uses where you don't care about the latent variables. I do care about the latent variables often, but I don't care about the number of clusters. What I want to know is that 2 points that really did come from the same component did get put in the same component most of the time in posterior inference. And so the small clusters that are screwing up the estimate of the number of clusters don't bother me, because if I pick 2 points at random, maybe they'll still end up being in the same cluster, because they're not in the small clusters usually. So I wonder if there are some other measures that do concentrate. For example, the L2 norm of the probability distribution over tables, which is basically asking if you pick two, the square of that is if you pick 2 points, what's the probability that they'll be in the same cluster?
Oh, I see what you're saying. Well, I think that if you randomly pick 2 points, the probability that they'll be, you're still going to have. Oh, let's see. No, I think you're right. I think so. So one thing which is often done is to sort of aggregate over multiple posterior samples, and so since which points are in the extra clusters are changing, and the number of points in the extra clusters is getting very, very small, then I think so. What you're saying is probably going to work just fine. Yeah.
So relatively simple clarification question.
Mm-hmm.
So your key theoretical result, if I understand correctly, says if you sample from the posterior and you sort of look how many clusters do you have, that even as n goes to infinity, you're likely to get something which is not the true number of clusters.
That's right.
However, you could ask a slightly different question, which is about the argmax. So if your new estimation procedure were to say, return to me the number of clusters which appears most often in samples from the posterior, would that be consistent?
Not in general, no. So our general theorem doesn't tell you the answer to that. We have looked at certain cases in which we know that that would not be consistent. So sort of the map estimate of the number of clusters is what you're asking about. And so, for example, in the one of the examples that we looked at in the paper was when the data comes from a univariate Gaussian with one component. It's basically a it was a standard normal distribution, and in fact, the posterior probability of one cluster went to 0. So the map was something bigger than 1. Well, so if the posterior probability of one component is going to 0, it couldn't be the map. It's a probability distribution. Well, okay, no, you're right. That's true. Yeah. So, yeah, I suppose that's true. It could be true. Yeah. So I'm not sure.
I have one more clarification question. So on your slide, you know, your statement is about generating from a finite mixture model, and then you had this bullet point where you said, you know, if it's generated from a DPM or, you know, not generated from a finite model, you're okay. And when you gave the talk, you said clearly for if data is generated from the Dirichlet process mixture, you're going to get consistency. But what if something's generated from what about that other class, right, which is not finite but does not have model match with the DPM? So hit me more with other specification or something like this.
So I didn't say you would get consistency. If the data is from a DPM, then the number of clusters is going to be diverging. So if you use a DPM, that posterior will be it will be correctly calibrated for that for the true number, but it's not going to be concentrating at is that
a finite number? No, I understand.
But
I mean, the distribution over the number of clusters is concentrating, right?
Not necessarily. I think in general, probably it's not. I think it's probably going to be, it's probably still going to stay diffuse. Yeah.
I guess maybe I can say my question one other way, which is, you said it's okay to use the Dirichlet process mixture model in cases where it's not generated from a finite mixture model. So I guess I'm saying, is that in all cases where it's not generated?
Oh, no. I mean, if it's if there's a match between the model distribution and the data, so the data is coming from a Dirichlet process mixture. Yeah.
Okay.
So thanks.
Thanks, Jeff. Okay, our next speaker is Vikash Mansinka, and he's going to be speaking on approximate Bayesian image interpretation via generative probabilistic graphics programs.
Thank you. So the idea that visual perception can be thought of as a kind of inverse of the causal processes of image formation has a long history, maybe going back to Helmholtz and Mach. A sort of computational version of it that we could think of vision as inverse graphics was popular in the early days of machine vision, and in fact also has informed the computational study of human vision. So this figure here is actually from a NIPS tutorial from about 15 years ago given by Dan Kirsten, where he was arguing that to try to explain some of the flexibility of human visual perception and also some of its interesting failure modes, it might be helpful to think of the visual system as inverting a process that goes from a scene description to an image, so trying to work backwards from the image to the scene description. Now, despite its sort of appealing intuition, outside of a few vision tasks like shape from shading, the idea of vision inverse graphics has been more of an inspiring metaphor than a viable engineering prescription. Most successful machine vision systems use bottom-up pattern recognition pipelines that really make little contact with the causal processes of image formation. Now, there have recently been a couple of interesting exceptions that, to borrow a phrase from Jeff Hinton, have started to take inverse graphics seriously. So one example comes from the work of Efros and Hoym and colleagues, where complex bottom-up searches are constrained by and also sometimes produce 3D surface information. There's also work by Jeff where generative models for pixels are learned, and although those models are based on sparse distributed representations, some key elements from computer graphics like transformation matrices are included. Today, I'm going to talk about a different approach called generative probabilistic graphics programming. Now, generative probabilistic graphics programming takes inverse graphics so seriously that in some sense we're taking it literally. The idea that we've found is that it's possible to solve some image interpretation problems by doing a direct approximate Bayesian inversion of a generative model for pixels. Now, our approach is based on 4 ideas. The first is probabilistic programming. So our generative models are written as probabilistic code, which generates scenes and then images that would be likely given those scenes. Now, we use that code to do inference, to interpret images, by relying on general automatic inference machinery that's built into modern probabilistic programming systems. So these first two ideas are necessary to take inverse graphics literally at all, but they're not enough to make it work. To actually make it work, we need to address a couple of basic issues that arise in this formulation. So the first is that it's hopeless to try to make a photorealistic image that perfectly explains all the image data that you're seeing. So we don't try. Instead, we use an approximate comparison of the rendering to the image data, which you can think of as a variant of approximate Bayesian computation. A second challenge is that even given those approximations, the energy landscape can sometimes be quite complex with many local minima. And so to address that, we use an adaptive smoothing technique that we call Bayesian relaxations, which I'll talk about later. So in this talk, I'm going to illustrate generative probabilistic graphics programming on two examples. One, reading obscured images of digits and letters, and two, finding 3D models of roads from single images. But first, a very brief review of probabilistic programming. So the idea in probabilistic programming is to represent probabilistic models as executable code. That code makes random choices for every latent variable in the probabilistic model. And then it's the job of general purpose inference machinery to work backwards from data to find the probable executions of your model program. Now, there's been a lot of activity recently in probabilistic programming, and much of that has been focused on making general purpose inference engines that aren't hopelessly inefficient. So the probabilistic graphics programs I'm going to present today are all written in Venture, a new probabilistic programming platform that's descended from Church. So for people who know Church, Venture retains its Turing completeness and expressiveness, but its inference engine tries to build on some key ideas from graphical models. In particular, it exploits an analogous notion to the Markov blanket of a random choice in a Bayes net to ensure that local changes to a hypothesis can be made efficiently. Each generative probabilistic graphics program fits the following basic template. There's a stochastic scene generator, which samples scenes. Then there's an approximate renderer, which takes a scene and some control variables x, which affect its fidelity, and produces an image. Then there's a stochastic comparison, which takes a rendered image, some control variables that affect its tolerance, and the input data, and produces a kind of likelihood term. So all three of these elements are written using probabilistic code, and I'm going to show several examples over the course of the talk. Taken together, they induce a probability model over scenes, control variables, rendered images, and data, which we can condition on data and turn the Bayesian crank, treating the control variables as nuisance parameters. And again, we're going to implement this Bayesian inference using just the automatic machinery in Venture, and in particular the simplest of its automatic inference mechanisms, which is just a local Metropolis Hastings sampler that randomly chooses aspects of the scene or the control variables to repropose. Our first illustration is on reading obscured text. We're going to focus on CAPTCHAs like the ones I'm showing here, in part because they're constructed to be difficult for optical character recognition systems to interpret, but also because we think they're an interesting step towards computational models for perceptual problems that are harder, but which our visual system solves remarkably well, like reading blurry text, or text that's imposed on a 3D surface that's been folded in some complex way. So here's a generative probabilistic graphics program for reading obscured text. We can understand it by breaking it down in terms of the template. So the top block of code is the stochastic scene generator, which generates a pool of glyphs, each of which might be present or absent in a given scene. They have a position, a size, a rotation, and an identity, that is what character or number the glyph stands for. There are some control variables. Crucially, in this case, these include blur parameters, so the bandwidths of Gaussian blurs or spatial low-pass filters that are applied to each letter and to the entire image. The renderer takes the blur parameters and all of the hypothesized scene elements and produces an image. It's implemented using a fast external 2D graphics library. And the stochastic comparison, in this case, is just a pixel-wise multivariate Gaussian, whose variance is one of the control variables. Now, you might think that inference in this hypothesis space is bound to struggle with local minima. And in fact, if you don't include the blur variables and do inference over on them, you'd be exactly right. So here I'm showing an input CAPTCHA along with 4 runs of the inference engine where the blur is fixed to 0 and the variance on the multivariate Gaussian is also fixed. the local minima that it finds aren't particularly helpful. Now here I'm showing a trajectory where we're doing inference over the per letter and global blurs and the variance of the multivariate Gaussian on the likelihood. And you can actually see over the course of inference many local minima escaped and a recurring trajectory for the blur, where when a letter is introduced, it'll often be blurred out until it's first localized and then later identified. So that kind of self-tuning annealing phenomenon is what we call Bayesian relaxation. Quantitatively, if you look at the reconstruction error on the y-axis as a function of the number of iterations on the x-axis, you can see that without Bayesian relaxation, these are the red curves, you typically get stuck in a local minimum, but sometimes you get lucky. And if you include it, you see more robust convergence. And if you drill down on the trajectories of the blur variables, you can see some of the annealing schedule automatically produced by inference that I mentioned earlier, where when a letter is introduced, the blur is raised, and then it tends to lower over the course of inference. Okay, so let's look at some empirical results. Here, the left column showing the input captchas, then some iterations, intermediate iterations of the inference engine, along with the final parse. On the second row, we're seeing a real-world captcha from TurboTax, where the distortions aren't actually part of the underlying generative model. So the circles, the white circles that are removed from the letters, have to be treated as noise by the model. The AOL captcha below it has per-letter rotation, which wasn't originally in our model, but we were able to add it with just one additional line of probabilistic code and a few additional lines in the supporting rendering software. On the bottom, I'm showing a synthetic captcha where the system fails. So that's actually due to the strong overlap between the X and the W. So on typical runs, sometimes it'll find both letters, but there's a reasonable probability it'll only find one or the other. Okay, now let's look at a richer example. So here I'm showing video from a vehicle-mounted camera driving down a forest road. And the task is going to be to find a 3D model of the roadway, including the locations of the lanes. We're going to baseline ourselves against a typical bottom-up system from robotics, which actually requires the extrinsic camera parameters, so the prior information about the 3D geometry, and produces 2D outputs. So our ultimate error comparison is just going to be in 2D pixel space. Here's the probabilistic graphics program we're going to use. So the first block is the scene generator, which generates the road's height and positions the lanes somewhere on it. The second block are the control variables, which I'll illustrate on the next slide. Then there's an approximate renderer, which in this case makes a call out to OpenGL, a popular 3D graphics library. And then there's a stochastic comparison, which implements an appearance model that I'll again show on the next slide. So here are some samples from the 3D scene prior rendered, just so you can get a sense of what the hypothesis space looks like. Now, the appearance model that we use is quite simplistic. We just quantize the input images using k-means, and we have a simple histogram over codebook IDs for each of the main regions in the segmentation induced by the scene. So for example, the road has some particular histogram on codebook IDs, similarly the right off-road region, and the stochastic comparison is just a multinomial likelihood with a smoothing term, a product over all those regions. And here are some results. So what I'm showing is the 3D interpretations overlaid on the input movie. Now, you can see that on some frames we do pretty well, and there are frames where we struggle, and in particular, those frames tend to violate the assumptions of our pretty simplistic generative model. Quantitatively, though, the accuracy is competitive with the bottom-up baseline, even if we only train the appearance models on a single input image. It's also, I think, illuminating to take a look at the posterior uncertainty produced by inference in our model. So in the left column, I'm showing a frame where the assumptions are violated because there's this crossing roadway. And on the bottom, you can see that there's actually a broader posterior that naturally arises from the Bayesian inference. So there's a mode where the lanes are supposed to be, and then additional possibilities that actually make sense if you look at the structure in the image. On the right, where the assumptions are better satisfied, you see a narrower posterior, although there is still a second mode that overlaps to some degree with the first. So this approach to solving vision problems is in early days, and scaling up is going to be interesting and probably quite challenging. But we think one appealing approach may be to combine the knowledge engineering that we've focused on so far with tools from machine learning. So, for example, we might try to learn parameterized generative models for appearance and shape, ranging from texture features, texture descriptors, to parameterized models for kind of superpixels painted on top of objects, and maybe ultimately even the parameters of procedural models, drawing on the procedural languages for shape that have emerged in the graphics community. We also might like to go beyond the simple generic MH inference schemes we've been using so far. So for example, it should be possible to learn bottom-up proposals trained on forward executions from the probabilistic graphics program. So the graphics program would generate the labeled data that the discriminative learning scheme would then use as training data to construct an inference algorithm. And there's a lot of precedent for this idea, from the Kinect system to the idea of recognition networks for inference in QMR-type Bayes nets, and even a really cool paper at NIPS on learning stochastic inverses by Andreas Stollmüller that gives a sort of modern take on a version of this idea. Okay, so in conclusion, we've seen that it's possible to solve some image interpretation problems just by trying to directly formulate them as approximately Bayesian inference over a graphics program. And the sort of key elements were probabilistic programming, so we could express models that literally invoke graphics software to model the conditional distributions, approximate inference engines, the idea of an approximate image comparison, incorporating the idea from approximate Bayesian computation, and a technique for adaptively smoothing the energy landscape as a byproduct of inference. Thank you very much.
Okay, before we take questions, can the spotlight presenters for this session line up over here? Thank you. So, questions for the speaker? Okay, I have a question for Kasia. So in terms of computational aspects of your method and how it scales with the size of the problem you're looking at, and especially in comparison to some of the competitor methods, can you comment a bit on that?
Sure. So the absolute wall clock runtime of our probabilistic programming system is certainly quite a bit slower. That number ranges from about 50x to bigger numbers, depending on the problem. I think that's typical for high-level languages, actually, before a serious performance engineering effort's been made. Scaling and dimensionality is, I think, a little bit more interesting, and there the results are a bit subtler. So, for example, if you crank up the complexity of the hypothesis space in the CAPTCHA problem, you actually don't see the time required for reliable convergence increasing rapidly with dimensionality. Something else appears to control the difficulty of the inference problem in that space. And ultimately, I think kind of those aspects of scaling are going to be more important for pushing kind of the richness of problems we can apply the method to, although performance engineering is also going to be important for, really real-world application.
Okay, oh, sorry, another question, yeah.
So you use some learning for the example of finding the road.
Yes.
To come back to the example of the handwritten character recognition.
Yeah.
In principle, you could learn a lot of priors. You could even learn the characters from enough examples. So how much do you think you need such learning, and how much do you think you can profit from learning technology on that side in the future?
So that's a very interesting question. I mean, I think ultimately it would be more satisfying if, and probably sort of make it easier to scale to a wider variety of images, if we're able to learn more of the constituents of the probabilistic graphics programs, especially the scene prior. That said, though, I sort of think it's going to be useful for us to alternate, as has been the case with other formalisms for knowledge representation in AI, between seeing what we can do in inference with a formalism that we've engineered, for sort of alternating work on that with pushing forward, trying to learn the representation itself.
Thank you.
Okay, let's thank Vikash again and move on to the spotlight presentations.